Okay, people, let's get started. I want to talk today. We're getting into the solutions part of the course now, and I want to talk about solutions to the biodiversity, food, and water problems. This is arguably technology. It's arguably just methods. None of this is particularly high-tech. The nice thing about these problems is that if it weren't for a climate problem, these wouldn't consume a generation, I suspect. And then I'll get on. We have, several lectures on the technology to solve the climate problem, because at the end of the day, that problem requires energy that doesn't emit, right? Unless you want to give up energy. Some do, but not the majority. Okay, so solving the biodiversity problem requires solving the climate and food problems in a particular way. And that's because habitat loss to agriculture is the greatest cause of extinction today. And with business as usual fossil emissions, climate change will be the greatest cause of extinctions in the future. So unless you get those two forces under control, unless you contain agricultural lands, and unless you rein in the projected climate change under business as usual, there's no way to solve the biodiversity problem. So you've already seen this slide, and this is just one of many calculations that you can make. Business as usual climate change. There's a bunch of studies that indicate you might lose a third of species. Agricultural expansion by 1.6 billion hectares at the expense of tropical forest. That's doubling cropland to meet a doubling of food demand would result in the loss of about 60% of the species, the terrestrial species, which in fact live in tropical forests. And so the solution is something like the Paris solution to climate change, which gets you down to 11% if you don't increase agricultural land. Now, 11% still sounds pretty bad, but it isn't 60%, right? So if you take what you can get. The 11%, though, is hundreds of thousands of species, but this is based on species area curves. In the next 100 years, if you look at historical rates of relaxation to the species area equilibrium, the destination, when you decrease a habitat, the species are going to go extinct over the long haul, but we have historical rates where we've done that 100 years ago or so, and we can see how fast the species go extinct. And so we might expect a few hundred extinctions of the mammal and bird species over the next 100 years. And so this does give us some time to develop new agricultural technology that would allow us to then reduce the amount of agricultural land we currently deploy. And so that's the hope for getting the number down a lot below hundreds of thousands of species and into the hundreds of species. This I've shown before. This is an environmental Kutznets curve. It's environmental damage versus per capita GDP. And then as people get rich, there's typically a lot of environmental damage, reaches a maximum. And then when they start to get really wealthy enough, the environmental damage is decreased because they invest in air pollution controls, and they invest in other things. These are the deforestation around the globe right now. And it kind of looks like a monotonically decreasing function, all right? The deforestation curve. And with a lot of these data, see that's zero? So all of this is negative. That is net reforestation. You hear a lot about deforestation, and tropical deforestation is a big problem. But there's a huge amount of net reforestation going on right now, and you can see it all over Latin America. And this is because people get too rich to live on crappy subsistence agricultural lands, and they move to the city and sell insurance or something. This is actually an interesting one. This is a meat consumption curve. And there is some hint of decline, right? Starting to be a hint of decline. But I'm going to talk more about the meat story later. because the meat story is one, as I've mentioned before in this course, that has changed in the last year, right? A lot. I've got some forecasts from lobbying organizations. These are trade associations that push meat into the market, right? Okay, so the historical story is that chicken is up and beef is declining, all right, globally. That's pretty interesting. So pork is relatively flat. Chicken is way, way up. Turkey's, I don't know what turkey's doing, but beef is moving. What country in the world has the highest turkey consumption per capita?
U.S.
What, U.S. somebody said? I thought it was Israel. That's that's what I read. At one point, yeah, we're like, yeah, I actually looked that up one Thanksgiving about 5 years ago, and it was Israel. Okay, maybe it's no longer true. This will not be on the final exam. All right, and this is of course a good deal because beef is got the 10 times the kilograms of CO2 per kilogram of food compared to chicken, okay? So that's, from a greenhouse perspective, this decline in beef consumption is pretty cool, right? Relative to chicken going up. And you remember this graph. Chicken requires 4 times less land than beef to grow. Now you say, well, chicken doesn't require any land. They grow them in coops, the poor chickens, you know? And the answer is, yeah, but you've got to grow the grain to feed the chickens, right? And so overall, chicken requires 4 times less land than beef does. So these trends in consumption of actual meat, historical trends, are encouraging, but of course not nearly fast enough. The meat demand until this year was expected to triple or quadruple by mid-century. And so that's larger than the replacement of beef by chicken historically. That bar there is 20 years old. Okay. Chicken also requires 4 times less water, right? And that's simply a reflection of the fact that most of the water in food is in the evapotranspiration from the crop plants that feed the meat. And so 4 times less land means 4 times less water. Okay, that's what that calculation is actually showing. Okay, so that's interesting. But is there a sort of a comprehensive plan to solve the food problem? And there is. There have been a lot of highly influential papers written on this. There was a big bolus of them between 10 and 6 years ago that are still sort of the go-to papers. One by Tillman here in 2011, and one by Foley in 2012 that I think is on the reading list, and so on. And so I'm going to go through, and they all agree, right? I'm going to go through what the solutions are, at least to the problem of meeting food demand on the current agricultural land. So GDP per capita triples, meat demand quadruples. So these are all from the papers, and this is quadruples from 2011. We're almost 10 years. I mean, we're only 8 years. We're 8 years after that. But you might think about meat demand as tripling from this point. A little closer to a tripling than it is to a quadrupling because we've already waited 10 years along the way to 2050 from the time these bullet points in this paper were constructed. Food demand doubles, and so most of the studies conclude. I read a huge number of them. There are truly a gigantic number of projections from UN groups and from NGOs and from academics on how to do this problem. And overwhelmingly they conclude that it should be possible to feed humanity on the existing agricultural land. Now that's not to say that there aren't some outlier papers that want to paint the story that you can't. So that, for instance, if historical yield improvements in crops that are 50 years long right, where we've been able to improve yields, if somehow that were to stop, then what I have to say today is wrong. Okay, so the claim that we know how to solve this is hostage to the continued successes of the plant breeders and agricultural practice developers. But I also think that it's probably a pretty safe statement because none of the solutions that I'm going to be talking about require anything particularly exotic. So none of them requires a breakthrough in GMOs, for instance, genetically modified plants. Right? All of this is just tried and true sort of stuff. So Foley has this 4-point solution. The paper's been cited, I don't know, several, like 5,000 or 10,000 times. And so he has a bunch of solutions, and it's worth reading because it's pedestrian but sensible. And so what does the solution consist of? Well, the first thing he says is that you need a 58% increase in production per unit land area by closing 95% of the existing gaps in yield. And here's a little map here about where those might be. But so, for example, in the case of corn, these are corn yields where 100% of the theoretical yield has been attained in a few parts of the world, but where there are big parts of the world in which the maize yields are still substantially beneath the yields that we know how to achieve. Now, why are they beneath them? And it's almost entirely because of the cost of fertilizer and how wealthy the people are growing the maize in this case. So this is primarily just fertilization, fertilizer application. Now, of course, fertilizer is a two-edged sword, but we're talking about the food problem right now. And so this shows that. If you ask, what's limiting maize currently? Green is that the yield ceiling is limited. That is, you've got theoretical best possible maize there for yielding grain per unit area. But these areas that were underutilized, you can see, are all red, and that's nutrients. All right. So they're nutrient deprived: phosphorus, nitrogen, potassium, PK fertilizer deprived. And so most of the yield gaps can be closed by increasing fertilizer and pesticide application. This is sort of the industrial farmer dream come true, right? By extending our admittedly controversial and possibly problematic system everywhere in the world. And there are these kinds of studies, like this one from Potter et al., about where the fertilizer needs to be applied. This is where it's currently applied, and you can see that it's applied here like crazy, and that's why we have a dead zone here, because all that fertilizer is rushing down into the Gulf. And there's a huge over-application here, a huge over-application here, a huge over-application here. But in sub-Saharan Africa, we have very, very light application. Across much of Latin America, we have very, very light application. And those are the areas where you can really get a lot of increased yield, which is good news, right? Because that's primarily where the demand increases are going to come as people become wealthier in those countries. And also in Africa in particular, as the population continues to grow. That's the last continent in which there is really substantial positive population growth still in the cards. It's not that there isn't population growth elsewhere, it's just that a lot of that is the historical legacy of age distributions that aren't in configuration yet. So they're young people dominated, but on average, women in most continents have 2 children or less, right? The average female does. And so that means that the populations have reached replacement or beneath. Most countries that are developed are now the people are all going extinct relatively rapidly because most women have under 2 children. So in Spain and in Italy, I think it's 1.2, in Russia it's about 1. And so their generations are halving each generation. There is also some possibility of increasing the the efficiency of water use, in particular in these arid regions in India and in Pakistan. We put in an awful lot of water per kilocalorie produced. And so there are, and this is a little pink over here, you'll see. There's a lot of improvement that can be made in a couple of areas in irrigation technology. This simply shows the yield per hectare as a function of water productivity. And water productivity is kilograms per cubic meter of water, kilograms of food per cubic meter of water. And so, and this is the yield in terms of kilograms per hectare. And what you can see here is that there are parts of the world that are under-yielding, all right? And those parts of the world have low water productivity. And so these are the targets, like those areas in India and Pakistan, for improving water productivity and then getting the yields up, all right? There's a lot of data on this. And we know how to do this. It's just that it's poverty eradication and economic development. And these are the hard problems that humanity has faced and have only gotten better on decadal time scales. All right, so Foley's solution number 2 should resonate with all of you. We want to decrease food waste by 14%. And this may seem like kind of a small number, 1/7 of the food waste. In particular, because 1/3 to half the food that we produce we never consume as a species. All right, so 1/3 to a half, think of it as 40%. In developing countries, 40% of the food is lost because of storage and transport problems. You can never get it to somebody's mouth in time. In developed countries, they're better at storage and transport, but the people themselves throw the food away. So they make too much and then throw it out, okay? And so this is the reason why in an affluent place like Princeton has been historically, why there's so much focus on food waste. So it'd be a good idea, right, if we didn't do this. And 14% is a realistic number, probably, given how resistant people are to taking responsibility for this sort of thing. Foley's third solution is for moderate shifts in diets, okay? This is food production area as a fraction of total cropland, with the remainder being animal feed production land. So when you look at cropland, you can either say it's human or animal food. That's 100% human food, and that's 100% animal food. Down there, you can see the blue parts of the world, all right, where we're growing grain to feed cattle, to feed ourselves, right? That's what we're doing here. And there are other parts of the world where there are rangelands. All of sub-Saharan Africa is primarily growing cropland to feed people. And if you have animals, they're not being fed crops that grow on cropland. They're being fed plants that grow on rangeland. That's why the American West has a lot of red in it. But you'll see a lot of poor countries have this sort of thing. And so the idea is that perhaps we could change the diets of the affluent. All right, that's the idea. Change the diets of the affluent. And as you all know, if we could, snap our fingers and make everybody in the world vegan, this problem would go away. All right, but that's turned out to be really hard to do. It's within the genetic plasticity of the human species because different cultures have already gotten there. So Hindu culture in India is just overwhelmingly vegetarian already. And as Hindus become wealthy, they do indeed consume more food, and they even consume more protein, just not more animal protein. So Foley has a very specific projection where he wants to take 16 different crops and shift them to 100% people food as opposed to beef food, and that means including feedlot beef in the U.S., which politically would have been an extraordinarily hard lift. However, this is one of many analyses I pulled off the web last week, and they all look like this, right? And so you take groups that are either pushing meat alternatives or that are meat industry groups sounding the alarm about meat alternatives. And what I like is that they agree on the forecasts, okay? I told you before that the Impossible Burger Company was the #1 IPO in the U.S. this year, beat all the tech IPOs. And so this is the kind of forecast that has them wigged out. This is 2025 to 2040, and with a tripling from 2020 to 2050, you get a 50% increase over that 15-year period from 1200 to 1800. And so that's the historical demand. And notice that conventional meat is down, actually declines. They're all now projecting conventional meat to decline in absolute terms globally, because people are shifting so rapidly to meat substitutes as they become better. And some of these meat substitutes are, from a greenhouse perspective, really pretty good. Any of them that are grown entirely from processed plant materials are pretty good from a greenhouse perspective, certainly relative to the beef that they're replacing. There are also vat-grown alternatives that are starting, where you actually grow cultured animal cells in a lab on a matrix of something like collagen to give it texture. And these have not penetrated the market yet. These would actually be lab-grown beef. And I know of no studies that have actually been done on lab-grown beef, because there's a lot of energy and stuff. You got to keep it warm, you got to do all this stuff, right? So, whereas you don't if you're simply processing plant stuff that you've harvested to make a meat substitute like an Impossible Burger. And so this decline, right, is extraordinary. And that's a decline that is, on the order of half over this 15-year period, all right? So what's being forecasted now by this industry is a collapse in global demand for meat. And so I think this story, maybe this is wrong, but it's a really interesting change in the narrative. And so if this were to happen, it would do a lot for the nexus problems. It would largely solve, more than anything else, it would solve the food problem, because you get a decline in meat, not an increase in meat. It would then free up pasture land and cropland for other uses, right? Because so much cropland now, about 20%, goes into animal feed, and all of that rangeland, which is double the cropland, could go into other purposes. 1 billion hectares of the rangelands is as arable and as rain-fed as our cropland right now. It's just cropland with alternative uses, mostly in rich countries. And all of that land could be used, for instance, to grow trees. And that actually is a way to get 10 gigatons of reforestation without harming the food system. So I think this is a really interesting technological development that I certainly didn't see coming. There's an article in today's New York Times, the business section, in fact, where they were astonished to find out that 98% of Impossible Burger and one other company's food is being sold to non-vegetarians. All right, so they expected this to be a vegetarian specialty sort of niche. Vegetarians secretly craving the taste of a hamburger, right? And it turns out that most meat lovers just would rather not eat meat, right? And which is weird because it's not like it costs less yet. right? And if you go get an Impossible, I've been told this, I've never had one, but if you get an Impossible Whopper, you have to pay an extra buck relative to the beef. And people are in fact doing this anyway. The Impossible Burger I bought cost, it was $8.50 for a 10-ounce package. All right, so I mean, an extraordinary price per pound, right? If you were buying beef, so people are paying a premium for this stuff, and it's going to get cheaper than beef. That's the thing. Everybody, all the trade groups say it's going to get way cheaper than beef. So I think this is nifty, and it could make fundamentally the nexus itself much easier to solve. She helps the biodiversity problem a lot by taking pressure off deforestation. It helps the climate problem a lot by allowing 10 gigaton scale natural climate solutions instead of 2 gigaton scale natural climate solutions without harming the food problem. It helps the food problem a lot by decreasing substantially the projected increase in calorie demand by 2050 and maybe making it flat or even causing it to decrease. It helps even the water problem. So, but not as much, right? It helps the water problem, perhaps, because it decreases the climate change, right? But it doesn't otherwise help the water problem that much. So anyway, this is neat. So that's Foley's solution. He got there, and many others have gotten there without genetic engineering and without the Impossible Burger. And of course, we do have genetic engineering, and we do have the Impossible Burger. And so I think I'm not feeling as freaked out about this one. But we haven't talked about organic farming. We've talked about big industrial farming, and this is a concern for a lot of people. We haven't talked about slow food, locavory. I don't know if this is a word, but it should be eating local, right? And make no mistake, people care about these things. Not just for nexus problem reasons, but because in talking to people who are passionate about these issues, what they love is the community building that comes from this, right? So this was a way to build a local community for people. We haven't talked about corn, which is of course not so good for us in processed form. Sugar, which is certainly not so good for us. Obesity, which is an epidemic increasingly worldwide, diabetes, which comes from obesity, insecticides, which are demonstrably poisonous, but we have to use them to actually maintain the food system we now have. We have a food system where if we didn't use a lot of these things that are bad for us, herbicides and insecticides, a large fraction of humanity would starve to death. All right, so we're kind of extended on the system already. Haven't talked about dead zones. We haven't talked about genetically modified organisms and whether or not they're a good idea or a bad idea. And we haven't talked about biofuels that compete for with cropland. So there are a lot of other issues that are outside of this full business. But as I said, so is the Impossible Burger. Does anybody? I'm just curious. Let's show of hands. Who is concerned? Who wants to limit the development of GMOs in the food system? Just raise your hands. It's entirely okay to do it. Yeah. So this is not a big issue in the U.S. Now maybe if I asked you to get out your clickers and so you'd have a different story. But if you go to the UK, and if I give a talk like this, all of the students are freaked out about GMOs, right? It's become really an issue in some parts of the world, but it's strangely passed the US by. Actually, why don't we get out your clickers? I'm curious. Okay. Yes, you're concerned about GMOs, and you really think, based on what you know today, we ought to limit them in the diet. Or B, no, you're not really concerned about GMOs. You think that the issues that are involved are less than other issues that you have to deal with anyway, right? Like that's your thing. push buttons.
B is not concerned.
B is not concerned, or just, of limited concern, right? It's like, I have other things to worry about that are more concerning. And A is, no, this is really an issue I want to pay attention to. Okay? Yeah, let it get into it. Somebody click something. I want it to get to 100 at least. Come on. All right, we're going to put it anyway. So it's a quarter and 3/4. And so that's kind of what I expected. That's what it's been in the past. And if you do that in the UK, it's reversed and then some. All right. So I think that's interesting. That's it. It's like, what are young people worried about? Okay. I want to talk a little bit about the water problem. There is a huge amount of work on the water problem. This is a good source if you're looking into it. Water for food, water for life. There are many such reports, but this one is, I think, the most authoritative. It's now old, but this technology has not moved that far, that fast. We really do know how to solve the water problem, and we just haven't yet. So the water problem, 50 years ago, water withdrawals were 1/3 of today's. So how much water we pull out of rivers was 1/3 what it is today. So that's increased a lot. And so now many rivers are insufficient, really, for those withdrawals. Some rivers don't make it to the sea at all anymore, all right? And with today's water use efficiencies, withdrawals will have to increase by about 80% by 2050. Now, I want to be clear about a difference that Catherine Rimaki didn't emphasize, and that's the difference between water consumption and water withdrawals. So you can withdraw water and put it back after you've used it, all right? So she showed that industry was a great big user of water that rivaled agriculture. And that's true of withdrawals, but it's not true of consumption. So what industry does is they primarily use it for power plant cooling. They pull water in, and they use it to cool some sort of a waste stream, all right? Use it to keep the plant cool. And some of that water gets evaporated, but usually it just goes up in temperature a bit. Right? It's like a radiator in your car. Right? Keeps the machine cool enough to run, so it doesn't melt itself, right? Turbines are incredibly hot things. Turbines are actually amazing. The interior temperature of a turbine already is beyond the melting point of the materials that make the turbine. And it only even works because you run liquid fuels over the turbine blades to keep cooling them inside this fire that would melt them otherwise. And so you need a lot of external cooling too, right? And certainly the nuclear reactor, if you don't cool it, it goes up and kills everybody and wrecks the whole world. And so you have to cool those things. But most of the water is just raised in temperature a few degrees. It isn't turned into steam. And so it gets dumped back in the river. And there are some issues associated with that. It's now warmer water relative to the way it used to be. But the actual withdrawals from the power sector are very small. In contrast, irrigation actually consumes the water. So the water that's withdrawn for irrigation goes into the atmosphere through the plant's leaves and actually from the soil directly into the atmosphere. So if you look at consumption, 75% of global water consumption is due to agriculture. Right? It's essentially an agriculture problem, an irrigated agriculture problem, not a, right? If you look at global flux, agriculture even dominates more because the rain is returned, right, through plants. But irrigated agriculture is 75% of human water consumption. All right, so 75% of the increased food demand can be met on rain-fed lands. 3/4, but that leaves 25% for irrigated agriculture, right? Which is then the dominant source of human water land use. But 3/4 of the remaining food demand can be met by increasing water productivity on those irrigated lands. That is better application of the water so that it gets into plant yield and doesn't just go straight to the atmosphere. And this leaves just a small amount, 1/4 of a quarter, for increased irrigation. So we're not going to have to expand irrigation very much as a species, all right? Which is probably a pretty good thing. So the water problem is about more efficient use of our current irrigated resources, all right? And we'll talk about the policies that lead to that. This is a slide that's kind of busy, and this just comes from the Molden report that has been so influential. And basically, what it shows, you can sort of look at this at your leisure. Green are rain-fed areas. Purple is the difference between optimistic and pessimistic scenarios for 2050 need. Blue is irrigated area. And there are a whole bunch of different scenarios. That's today, and this is mid-century under a bunch of different scenarios. And the thing I want you to focus on is just that not much happens to the blue. Right? There's one scenario here where they just said, well, let's suppose somehow we try to expand irrigated area. Then it goes up a bit. But mostly, water experts don't think there's going to be a big increase in irrigated area in the world, period, by mid-century. Which was a surprise to me when I first looked into this. I thought that would happen. So this is a table also from Molden. Scope for increased productivity in rain-fed areas, scope for improved productivity in irrigated areas, and scope for irrigated area expansion. In sub-Saharan Africa, there is actually, that's where you could still expand irrigated agriculture. Everywhere else, not so much. If for improved productivity in rain-fed areas, that's also very high in sub-Saharan Africa where the fertilizer use is low. And this pretty much correlates with places that are still developing. It's all about fertilizer application. This is for scope of improved productivity in irrigated areas. That's in particular high in South and East Asia. Remember that picture that I showed before of India and Pakistan having really low crop yields per unit of water produced on irrigated land. Remember, it was red over India and Pakistan. That's what that's showing there. So to do this, we don't need new technologies. It turns out that the technologies that we have used historically are really inefficient. So what we do is we move water in canals. The water evaporates from the canals. It gets soaked into the soil in the canals and percolates in groundwater in places where there is water so that it never gets to the places where there isn't. And then it's just sort of dumped on the cropland where most of it doesn't get into a plant. And so the efficiencies for a surface, if it gets to the cropland and you just flood the field, which is what's been done since ancient times, about 60% of it makes it into a crop, but that leaves 40% that doesn't. If you use a sprinkler, you can get that up to 75%. And if you do drip irrigation, like they do in the Negev and a lot of other places where you have hoses running down the rows of plants and drips are going by each plant, you can get that up to 95%. And that's what this thing is showing here. So between fixing irrigation transport conduits, replacing open ditches with pipes, sometimes as simple as putting some clay along the walls of an irrigation ditch so that the water doesn't soak in as much, and then changing the efficiency of the irrigation method, which admittedly takes capital, right? Capital that pays for itself. That's why you see in rich countries crop circles done by sprinklers, right? But nonetheless, you can really increase this well. People often ask about desalination. Desal is coming a lot, but it's still really, really, really expensive relative to rain, all right? It's just really expensive. And relative to conventional irrigation. It's fine for people to drink if you don't, if you don't have enough water to drink. You'll pay the money for desal, but there's no way we're running this. So Moshe Dayan, who I think is here, was an Israeli general, and there was always talk that the Israeli-Arab conflict was primarily about the Jordan River, because they were fighting mostly with across the river. And he said that's ridiculous. For the price of 1 week's fighting, you could build 5 desalination plants, right? And which would have covered all of his production. And so his argument is nobody's ever going for war over water. You might get political destabilization because of climate change related water issues, and then you might go to war over that, but you're not actually fighting over the water because it's a cheaper way out. All right, so no tube technology is actually needed. You can use crop breeding. You don't need to use genetic engineering. You don't need to invent a fundamentally new water system. There is a huge amount of technological work on improving desal, which is great, but it's not going to fundamentally affect the water problem because 75% of consumption is irrigated agriculture, and you're not going to desalinate that water. The impediments that we have, the real water problems that we have locally, are political, not really technological. And a good example is the Colorado River Basin, where a combination of water policies has led to overexploitation of the Colorado River, so much so that it stopped reaching the sea quite some time ago. This is the Colorado River flow, and it just kind of stopped, right? And this is the outlet of the Colorado River. And then a few years back, 2014, the Environmental Defense Fund and a bunch of other groups got together, and they decided to arrange a week in which landowners coordinated not to use irrigated water during a period, and they let the Colorado River go back to the sea. And what was interesting is they didn't have a celebration, but it turned out that the Mexican families on the other side of the border all showed up, and there was this like spontaneous festival that, from pent-up demand, everybody remembered the river being there. And so it's really interesting to ask, how would you be able to restore the Colorado, and would it actually damage the players along the Colorado economically? And the answer is encouraging, in that it would be possible to restore the Colorado. Not just historical levels of flow, but that doesn't really matter because the flow of the Colorado River was dominated by flood stages when snowmelt from the Sierras and Rockies made the river rage. If you just want to make the river flow the way it did 95% of the time, you could do so without decreasing agricultural yields in any of the irrigated lands along it. All you have to do is change water policies. The water policies are crazy, and I'll get to those in a minute. This is one really good example. Alfalfa is the most water-hungry crop, and this is one of that's like the highest per unit land area alfalfa growing place in the country. All right, which is like, look at that. You know what that place is like? There's like no water there, right? Why is that? It's because of historical water rights. Because of the way these rights were established, landowners either use their water allocation in full or they lose it. And so they put alfalfa on there to use up all the water so that they safeguard their historic water right. And if you then, so there's a consortium of really wealthy people in California who are considering just buying the whole thing, right? And so you could then just grow something sensible on that and release enough water to allow the Colorado River to flow again. Another good example here about the cost of the Colorado river policies is this Lake Mead example. Lake Mead is losing water. Lake Mead supplies most of the water right now for Los Angeles. Anybody live in Los Angeles? Anybody? And so this is an issue, right? You hear about water in California all the time. They tell you to, really watch. You got to have a low-flow toilet. You got all this stuff, right? And the answer is that low-flow toilet is doing buckets for the water in California. What it's doing is it's saving the water company some money because that gray water system is being reused in LA. It's going to a sewage treatment plant that's coming back into the system. It's true that watering your lawn actually goes into the atmosphere, and that is a marginal cost. But overwhelmingly, the reason there's a water problem in LA is not the use of the people in LA, it's the agriculture upstream from LA. And what it's done is there's so much that's withdrawn for agriculture that Lake Mead, which is this giant reservoir created by Hoover Dam, has been falling historically. And the big water uptakes for Lake Mead have, this is the fall, have become exposed, so they no longer even work. And so they had to build new water uptakes at the cost of many hundreds of millions of dollars, just as the lake continues to fall, and it's going to continue until water policies are changed. Okay, policies that work. Water cap and trade. Most places with low irrigation efficiency have either no regulation or historic water rights. A non-transferable right for a landowner to withdraw a set amount of water. Some have these incomprehensible use it or lose it laws. You can't sell that right to anybody else. You can't sell water to anybody else. You just have the right for it. So instead, if you give each landowner a water entitlement to a set fraction of stream or groundwater with the ability to sell unused water, it is a giveaway primarily to wealthy agribusinesses and wealthy families that own huge, amounts of water rights. But nonetheless, if you give them this entitlement with the ability to sell unused water, all of a sudden you change their individual incentives from being, I've got to use this water because I don't want to lose the right, to I'm going to save water because then I can sell it to somebody else. All right? And that turns out to be, that little change turns out to be unbelievably successful. You can get 100-fold decrease in water use that way. All right? There are historical examples of 100-fold decreases, lots of examples of a 10-fold decrease, just because people care about selling the unused water. Australia now is the one country in the world where this is done more than anywhere else, and 30% of water is now traded. Okay, this is the list of things that I want you to know from the lecture. I think they're pretty self-explanatory. One of these days I'm going to get to Princeton's fossil fuel news. I thought it was going to be today, but it didn't. It's because the Impossible Burger took up my extra time. See you next time.